Welcome to 55th lecture in the course of Industrial Engineering and Operations Research. We are discussing queuing theory and we have already given 4 talks. Now this is the concluding talk on that topic. So we make queuing decision models. Queuing decision models focus on making optimal decisions about managing queues and service systems to improve performance, reduce waiting times and increase customer satisfaction. These are the objectives of queuing decision models. These models combine queuing theory with decision making tools to guide how to design or control service systems. So in queuing decision models, queuing theory concepts will be used, but also we will make decision making tools. So these queuing decision models assist in many things. One is the service capacity decisions, like what should be your service capacity. For example, how many servers should be deployed? That is a very pertinent question. Like in a booking counter, how many counters should be there at any station? How many booking counters should be there? Many things. Or how many computers should be purchased with operators if something is being done. Many such type of things can be done. When to add or remove service counters, that decision also has to be taken. That maybe in the morning time, if there is a rush, more counters can be there. In the evening time, counters can be reduced and vice versa, those type of things. Then queue discipline decisions. Even we make this type of decision that which priority rules should be used. For example, it should be first come first served or it should be some priority queue. Should some customers be prioritized or given faster service? Then routing and scheduling, how to assign arriving customers to different service channels or queues, how they should be assigned. You might have seen at the airport, when we go, then some security person, he says that, okay sir, please go that side. Instead of this side, you go that side. Okay, so that type of thing also is done. Scheduling server availability during peak and off-peak times. And examples are that like hospital emergency room, here we prioritize patient by severity to minimize critical waiting. Then manufacturing systems, deciding buffer sizes and processing stations to optimize throughput and minimize delays. In manufacturing systems also we decide that extra buffer. And then we use obviously the cost models are also part of queuing decision models. Cost models quantifies the total cost involved in operating a system. It assists in finding the most cost effective way to design or operate a system. Cost components are operating cost, which includes labor cost, equipment and utilities. Then waiting costs, that customers waiting time, penalties for delay, these costs are also there. Service cost, cost of server or resources used. And then penalty cost, costs from poor service, lost customer or system failures. So like that we can have these type of costs we can identify. Example, in a queuing system, the cost model might include the cost of staffing more servers versus the cost incurred from customers waiting too long, leading to dissatisfaction or lost business. So we have to optimize. If you keep more servers, the cost will increase, but the customer satisfaction may be better. But you know that you can't afford too much cost also, so there is need to optimize. By modeling these costs, the optimal number of servers can be decided. So now I am just giving a simple example for your understanding. Example is that a single server service center receives customer at a rate of 10 per hour poison arrival. That means inter-arrival time is exponential. I have taken a single server model because most of the competitive exams only single server problems come, and of course that you can do multi-solver. Today we will discuss some multi-solver problem also, but you know, first just see that a single solver service center is huge customer at a rate of 10 per hour. So here we will say lambda equal to 10 per hour. So lambda is given. The average service rate is 12 per hour, exponential service. So service rate is also exponential, inter-arrival time is also exponential, and it will be this one, okay. Mu service rate is 12 per hour. In a single server, of course, service rate should always be more than the arrival rate, otherwise the queue will become unsteady, that otherwise you will not get a steady state. Now customer waiting cost is rupees 20 per customer per hour. Suppose a customer waits for 1 hour, he keeps sitting there, then you can count that he takes 20. Maybe even if he doesn't demand any extra money, but suppose extra customer is there, he is sitting in your place, he is occupying, he is getting AC and other things. So that cost will also can be counted, okay. He may drink water, he may take something, so that cost more it is, this one keeps waiting, naturally there is a cost involved here also. And server cost is rupees 100 per hour, let us say server cost is 100 per hour. Determine the utilization factor, expected number of customers in the system, average time a customer spends in the system, then total expected cost per hour. So let us do it one by one. In these 3 questions you already have done, they are just based on the queuing theory, only the cost element I have added in the 4th part. So first is that arrival rate is 10 customers per hour, service rate is 12 customers per hour, waiting in system cost per customer per hour is rupees 20 and server cost per hour rupees 100. So utilization factor, there is a straight formula, rho is equal to lambda by mu, that it is come 10 by 12, that means 0.8333, that means 83.33% utilization, 83.33% utilization. Expected number of customers in the system, LS is equal to rho divided by 1 minus rho. Rho is the utilization factor, you put this value 0.833, 1 minus 0.833, and which comes out to be 4.99, okay. You can say something like 5 customers, but we generally express in the fraction only because it is the average number. It is not that you will always get 5 customers, sometimes they may be 7, sometimes they may be 10 also, and sometimes 1 or 2, but average is 4.99. Average time in system by Little's formula, is it not little? Little doesn't mean that is small, little means that the person of that person who wrote a paper on this, Little's formula. So W is equal to waiting time in the system, L divided by lambda, just divided by arrival rate. So 4.99 divided by 10, okay. So this becomes 0.4999 hours, and in minutes it will be 29.94 minutes. Now waiting cost per hour is equal to L into cost per customer, okay. So I am taking system length, that suppose he remains in the system also, then we assume that that cost also goes. So 4.99 is the system length, and this is means person length of the system, and then multiplied by 20, okay, because 20 per hour, okay. So that means rupees 99.8, and total cost is equal to rupees 99.8 plus server cost, that means 99.8 plus 100, that means 199.8. So you have to count that when you run a business, then you don't just see the only the server cost, rather you have to see that how much cost of that extra is there, okay, waiting etc. So that means it becomes 199.8 type this one per hour. Now let us continue about queuing decision model. So there is one term called aspiration level model. It is a type of decision making model where the decision maker sets a target or desired level, aspiration level, that is called aspiration level, for certain performance measures such as waiting time. For example, they say okay, waiting time should not be more than 3 minutes. Okay. So, that means this is your aspiration level. Queue length or system cost. Then it attempts to adjust system parameters like service rate, number of servers, etc., to meet or exceed that level. So, that is means then first they set some aspiration level, then they try to adjust. Okay. So, aspiration level is basically a predefined acceptable limit for performance. For example, average waiting time should not exceed 5 minutes, that is aspiration level. Average waiting time should not exceed 5 minutes. What are the decision variables? Parameters which are under your control, number of servers, you are free to increase or decrease the server. Service rate can be enhanced, that can be changed to reach the aspiration level. Optimization is goal oriented, unlike traditional cost model that aim to minimize total cost. Your traditional cost models will try to minimize total cost, but aspiration level model seeks to satisfy service level expectation. Cost is secondary. First they say that customer should be satisfied. This may not be purely cost optimal. So, from cost point of view, this may not be optimal. Usage of aspiration level models in service design, like in banks, hospital, call centers, or in public service system where user satisfaction is prioritized. So, here let us give that one example, simple example. A manager wants to ensure that customers do not have to wait longer than 6 minutes on an average. So, 6 minute waiting is allowed, but not more than that. The arrival rate is 10 customers per hour. What should be the minimum service rate? So, if you want to find out, lambda is given, that is 10 customers per hour, W is equal to 6 minutes is equal to 0.1 hour, that is aspiration level for average time in system. So, we have included this in the system actually in this. Here language becomes of course very important. Sometimes if you do say mistake that WQ may be different, waiting time in queue or waiting time in the system, that has to be understood. Sometimes even the questions also are not very clear. This type of problem I am seeing in the books, but you have to be alert and you have to understand, and you can, if there is a opportunity to in descriptive type papers, you can of course mention that this is your assumption and this is that thing. So, here we are telling W is equal to 1 divided by mu minus lambda. Okay. That means this is if I say that if I divide it by mu, so this becomes 1 by mu and 1 minus rho. Okay. That is waiting time in the system formula. Few minutes before I told that formula LS is equal to rho divided by 1 minus rho. LS is equal to rho divided by 1 minus rho. In terms of lambda and mu, this will be lambda by mu divided by 1 minus basically rho only. So, therefore, by Little's formula, Ws basically more precisely Ws will be LS by lambda, that means 1 by mu and divided by 1 minus rho. This is what I have written here. So, this is like that. So, if somebody takes waiting time in queue, then of course, the answer will be different. Okay. So, we are taking waiting time in the whole system. Okay. So, this is a W value is given that waiting time should not exceed 0.1. So, let us say that suppose it is 0.1 border case, then 0.1 divided by 1 by mu minus 10, lambda is known, mu is unknown. So, we solve that and we see that it comes out to be mu is equal to 20. So, this is 20 per hour. Okay. We can say 20 customers per hour. So, to meet the expiration level of 6 minutes maximum waiting, the service rate mu must be at least 20 customers per hour. Whatever you want to do, that you can do that way. Otherwise, if it is not possible by single station, you can open the multiple stations. So, let me just tell about multi-server model. This is I have taken from the book of H.A. Taha only, and you can do that. I am not going to too much detail, but I am telling that how the multi-server model will go. If we take a general case and let us say that arrival is system dependent, that means we have got lambda n. So, arrival rate is dependent on the system and n is greater or equal to 0, and then mu n is equal to service rate, which is also variable. So, let us say service for one system is basically mu. So, if n is smaller than C, okay, C is the number of parallel servers, okay, that means this is C. Suppose there are 3 parallel stations, okay. So, if n is less or equal to C, then the service rate will be mu n is equal to n mu, because suppose there is one customer in the system, he will go here. Suppose there are 2 customers, then they will go there, like that. But service rate will of course saturate, because you cannot have more than 3 mu or more than C mu if there are C stations. So, therefore, we say that mu n is equal to C mu if n is greater than C. So, by generalized formula, now suppose I say that lambda is not dependent on the system, lambda is always constant, lambda n is equal to lambda. So, P n is equal to lambda n, and we can put these values P0, that is the generalized formula. You remember that I talked and I told the general formula was like this: lambda 0 P0 is equal to mu 1 P1, and Pn is equal to lambda n minus 1, lambda n minus 2 up to lambda 0, here mu n minus 1 up to mu n into P0, n is equal to 1, 2, 3. So, we put that formula only, Pn is equal to lambda n mu into 2 mu. I can keep putting the values, okay. So, suppose 1 is there, so this is mu, but then 2 mu, then 3 mu, and up to, of course, you get up to n mu, then you get saturated also, and P0 is equal to this one. So, this can become, suppose n is smaller than C, up to that you have got this formula, lambda n factorial n mu to the power n and P0. And if you have n greater than C, then you can put lambda n and you can put the other values n 2 mu, C minus 1, C mu, n minus C plus 1. You can work out this thing. You can pause your video, note down this expression, and yourself can verify. This is P0. So, this will be lambda n divided by factorial C, C to the power n minus C mu n P0, n greater than 0. We can make some notation. Suppose we can say rho is equal to lambda by mu, and here of course we are telling not that rho should be less than 1, but rho by C must be equal to less than 1 for making the system steady, okay, because there are many channels. Na? So, suppose it is not that if arrival rate is more than service rate, in this case it will not become unsteady, because as long as there is another server to support. So, this Pn expressions are there for both the cases. Then we simple law of probability that n is equal to 0 to infinity, n is the number of customers in the system, and up to infinity n is equal to 0 to infinity is equal to and Pn, that means sum all the probabilities, this should be equal to 1. So, by that you can find out P0. You can find out numerically also if there are finite computation. So, by doing that procedure you get P is equal to this much, okay. I do not want that you should memorize this, but you can use it as something that if there is a question, then naturally this expression may be given to you, and P0 is equal to this much, rho by C is equal to 1. So, that formula has come. You can verify that it is basically the summation of the series and all these type of things. Otherwise, you will see later on some terms become very small and it can be truncated in numerical way also. And then of course, if I want to find out LQ, that number of Q length basically, so N is equal to C plus 1, because if there are C customers in the system, then there is no Q, because each one is getting service, because there are C stations, each customer is standing in front of those station. But if this is more than 1, then there will be waiting. So, N is equal to C plus 1 to infinity, and we have to say N minus C. Suppose N people are in system, in that you have to subtract the servers and into corresponding Pn. So, if you do that, you get this type of expression, P rho to the power C plus 1. In the denominator, we get C minus 1 factorial C minus rho square P 0. So, and then Ls is equal to, of course, Lq plus rho. So, apply Little's formula for finding out the waiting time and time in system. That can be done by Little's formula. So, this you can, of course, you can do like that. So, you can do this way. Okay. So, this is equal to that one. Okay, fine. Now, here, so this formula you can use for multi-channel. Okay. Let us do that now, some simple problems after doing that thing, which will help you in many exams. If the inter-arrival time is exponential and 10 customers per hour arrive in a bank, then the probability of no arrival of customer during a period of 10 minutes is, what is that question? So, here lambda is equal to 10 per hour, that means 1 by 6 per minute, 1 by 6 customers per minute. Okay. So, probability that t is smaller than 10 will be 1 minus e to the power minus lambda t. So, time is 10 minutes and this is 1 by c. So, you just see that here it is basically 1 minus e to the power minus lambda t. So, you have to use appropriate units. Okay. And so, both way, otherwise I could have kept lambda in hours only, but then time also you have to give in hours, so same thing comes. So, this is, and Pt greater than, so Pt greater than 10, that means no arrival of customer during a period of 10 minutes, that means time should be greater or equal to 10, we are finding out that. So, that is 1 minus this quantity, so that is 1 minus, that is e minus 10 to the power 10 by 6, e minus 10 by 6, and which becomes basically 0.1889. So, this becomes 0.1889. So, probability that no customer will arrive in this one, that 10 minutes is basically very small. Okay, because anyway that 10 per hour, that means basically in 6 minutes on an average you expect one customer. So, therefore, it is question is that sometime there is a no customer in 10 minutes, that is possible, there is a possibility, but it is 0.1889. Okay. So, that is what that this has come. Achha. By suppose the same problem is done by Poisson distribution, because Poisson distribution is there. So, P n t is equal to lambda t to the power n e minus lambda t factorial n is equal to 0, 1, 2, 3 discrete values. This perhaps you can memorize also. This is by Poisson distribution. This tells what is the probability of n number of customers in the system. That means lambda t to the power n 1 minus lambda t by factorial. So, here you put t is equal to 10. So, P 0 10 is equal to 10. This is n is 0. So, P 0 means there is no customer in the system. That means in the system there are 0 customers. So, P 0, so lambda t to the power 0 is 1 and factorial 0 is 1. So, you simply get e minus lambda t. Here you get e minus 10 by this 1.1889. So, basically you get same thing, that you know exponential distribution and Poisson distribution, they are basically two ways of saying the same thing. Of course, there we talk about inter-arrival time, there it is a continuous variable, here we have discrete variables, but you are getting the same answer. So, this is how that you have done. Okay. So, it is this you have done. Okay. And then let us say that we do one problem. A bank has one teller, customers arrive at a rate of 10 per hour Poisson distribution, and the teller serves them at a rate of 12 per hour exponential distribution. What is the average number of customers waiting in the queue? Okay. So, here lambda is equal to 10 customers per hour, mu is equal to 12 customers per hour, rho is equal to lambda by mu, that 10 by 12, that means 5 by 6. Now, LQ is equal to rho square by 1 minus rho. That is the thing, because we have said that LQ is equal to, I think we told LS is equal to LQ plus P, and I said that LS was rho by 1 minus rho. Okay. LS by rho, LS is equal to rho, LS is equal to rho by 1 minus rho. So, how do you find out LQ? LQ means LS minus rho, you subtract that. So, this is rho divided by 1 minus rho minus rho. So, this will become rho minus, so this will become rho square by 1 minus rho. So, you do that rho square divided by 1 minus rho, rho is equal to 5 by 6 square, and this is divided by 1 minus 5 by 6. So, this becomes 25 by 6 customers by calculation, 25 by 6 customers. So, LS is equal to LQ plus rho, that means 20 by 5 by 6 plus 5 by 6 is equal to 5 customers. Now, you want to find out waiting time in the system. So, WS is equal to 5 by Little's formula, 5 by lambda, and lambda was 10 customers per hour. So, answer will come in hour, and that comes out to be 0.5 hour. So, the waiting time is 0.5 per hour. This is by Little's formula. Okay. Little's formula, time, that is divide by lambda only, Little's formula, Little's formula. Okay. So, this is equal to this one. Okay. Little's formula. So, this his original paper also you can see in the Scholar Google, and you do that, but it is very simple, that just divide by lambda. Now, in there is something that finite waiting line model, also known as a finite queue model, is a type of queuing system where the number of potential customers or the system capacity is limited, unlike in finite queue models where an unlimited number of customers can join the line. The finite model considers practical constraints such as limited space, limited customer population, or restricted system capacity. In some books, you will get finite queuing table to solve. That means it is something different and little bit complicated, but you will get table. You need 3 inputs: size of the population n, the service factor x, and the number of parallel server m. This data is there, then you can get information from the tables. This I have taken from the book of Buffa and Serene. You can also see the book of Buffa and Serene, but you know that we will not teach in much detail. So, x is the service factor, x is equal to mean arrival rate per population level divided by mean arrival rate per population level plus service rate. Okay. So, mean waiting time is equal to mean waiting time plus 1 by service rate is equal to mean time in system. Okay. That means the same thing that we say that okay, waiting time WQ is equal to that one, and mean WQ plus 1 by mu is equal to WS. Mean number of units being served is equal to mean system length minus mean queue length is equal to H, and M minus H is equal to mean number of servers idle. So, this is okay. So, only this much I will tell that I will tell that there is a waiting line models also, finite waiting line model where is system, and there are waiting those tables. By that you can do. I just have given exposure. We will not go into that much detail, but in most times when you know that number is large, then people solve by infinite weighting line model, and this is what I have just told. So, we will conclude at this stage. Otherwise, basically queuing system itself is a very big topic, but we are concluding at this stage, and then we will study other things. Okay. Thank you very much for your attention.